So in the previous lecture, we talked a little bit about the origins of entropy and what sort of conceptual picture we should have for entropy. And now we're moving on to something called the standard molar entropy. And the standard molar entropy is just the entropy of 1 mole of a pure substance at 1 atmosphere and a temperature of 25 degrees Celsius. We can expect that if a molecule is more complicated, there's more ways, like if we took a big long molecule and had just a model kit, we could bend and shape that molecule in all kinds of different ways. So just think of that as a sort of configurations in a sense. It's more complicated than that, but bigger molecules will tend to have a higher standard molar entropy at any given temperature, just because they have more configurations that they can have. And that really boils down to rotations, vibrations, and other things like that. And so additionally, what we expect is the same trend that we've seen before. If we're dealing with the gaseous phase of a substance, it's going to have the highest entropy of the phases, and then the liquid, and then the solid being the least entropic. So let's take a standard reaction, just our AA plus BB to CC plus DD. And remember how we have done this with the delta H, delta G. In the past, we can also do it with delta S and these standard molar entropies. And we can find the entropy change in a particular reaction by just looking at the entropy of the products using their standard molar entropies and subtracting the entropy of all of the reactants. So if we look at what that change in entropy that we're going to get there, you just see the coefficient is multiplied by the entropy of that particular species. We start with just D, which is the product, and C, which is another product, minus B, and minus A, if you distributed that minus through. So it's just products minus reactants. The units, of course, are just joules per mole Kelvin, as we've used plenty of times in the past for entropy. Okay, so let's take a look at using the standard molar entropies to calculate the change in entropy in a particular reaction. So in this particular one, we're seeing N2O4 decompose down to NO2. And so to find delta S, it's just going to be 2 moles of the NO2 times the standard molar entropy of 240 joules per mole Kelvin. And since N2O4 just has a coefficient of 1, we just get 1 mole times 304.3 joules per mole Kelvin, which is N2O4's standard molar entropy. And just one thing to take note of, just remember that these values are just something that you're going to have, you're going to be given, or you'll have to look up maybe in Appendix B or in your book, but they're not something you have to memorize at all. That gives us an answer of 175.7 joules per Kelvin. Notice the moles will cancel out, so you're just left with joules per Kelvin. You need to always just make sure and check your answer, because it's easy when you're first doing these sometimes to flip things around. And so does the sign of delta S make sense? Going into this, we look at it, we have 1 mole of gas breaking down to 2 moles of gas. We should expect that that's going to have an increase in entropy for this system, and so a positive delta S makes sense. So let's look at another reaction. This is just the Haber-Bosch process. We've seen this quite a number of times through the semesters, and we want to calculate the delta S for this reaction. So if we look at the delta S values, or the entropy values that we could find in a table, we'd find that for ammonia it's 192.3 joules per mole Kelvin. Since we have a coefficient of 2 out in front, we should expect to get a 2 here as well. And then on the next one there, we've got minus the hydrogen, which has 130.6 joules per mole Kelvin standard molar entropy, and we subtract that one out. And then lastly, we have the nitrogen at 190.1.5. And since it only has 1 mole, I accidentally highlighted the wrong thing there. We would have 1 mole and 1 mole there, okay, since its coefficient's just 1 out in front. And so if we go ahead and look at the delta S overall for that, it's going to be minus 198.7 joules per Kelvin. And so does it make sense that we're going to a lower entropy, or entropy is decreasing in this case? Well, we started with 4 moles and we ended with 2 moles of gas. And so it seems consistent with what our expectation should be there. Okay, so here's a clicker question, just an example problem. And it says standard molar entropy for bromine is 245.46 joules per mole Kelvin at 25 C. Given that delta S is 104.58 joules per Kelvin, for the dissociation of 1 mole of Br2 into Br at 25 degrees Celsius, find the standard molar entropy for bromine gas at 25 C. So this is just looking at one unknown that we have in the problem. We know the overall delta S for the reaction, and we're supposed to use basically just our equation that we can generate here to find that one unknown. So we have Br2 going to 2 bromine atoms, and so we have basically 2 moles of X. We don't know what that entropy of formation is for that. And then we have 1 mole of 245.46 joules per mole Kelvin for bromine, as it's stated. And so we know that's the equation should govern it, and it tells us the delta S of the reaction is 104.58. So all we really need to do is just add that 245.46 joules per Kelvin that we're going to get there to the other side, and then divide all of that by 2. And so doing that, we're going to end up with a value of 175.02 joules per mole Kelvin, which matches up nicely with C. So one of the things that we see with entropy, and in reference to our second law of thermodynamics, so we see that the reactions are moving spontaneously to a state of minimum enthalpy and maximum entropy. And so we used delta G last semester to indicate whether a change is spontaneous, and we want to just take another look at that. We know delta G, when it's greater than 0 for reaction, it's not spontaneous. When it's equal to 0, we're at equilibrium. When it's less than 0, the reaction is going to be spontaneous. So how can we sort of verify how these conclusions were reached? Well, we're going to look a little bit at the first and second law of thermodynamics in order to do that. And the first law of thermodynamics is just that the energy of the system plus our surrounding is conserved. It's just conservation of energy there. And then the second law is just saying that any spontaneous process, the total entropy of the system plus its surroundings is always going to increase. So delta S is greater than 0 for any spontaneous process for the whole system plus surroundings. So nailing this down to a bit more of a quantitative perspective, let's say that delta S total is just delta S of the system plus delta S of the surroundings. And so taking our picture, delta S total is greater than 0. We've said that's a spontaneous process. Delta S total is less than 0. That's a non-spontaneous process. And if delta S total equals 0, then we're at equilibrium. And so we want to figure out a way that we can actually calculate delta S total. So delta S of the system is just the entropy of the reaction that we have been practicing calculating. And delta S of the surroundings, I'm sort of providing here without a proof of how we're doing this, but hopefully you can see that it would make sense that delta S of the surroundings is going to be equal to minus the delta H over the temperature of the surroundings. And that's because delta H, well, what if delta H was negative? That means it's an exothermic reaction, and we expect that the heat release there is going to make the whole system, is going to basically increase the entropy of our surroundings. So if the system undergoes an exothermic reaction, it heats the surroundings, and so we should get an increase in entropy. And that's what we see with that negative delta H relationship there. And if we have a endothermic reaction, of course, it's going to be positive. It's going to pull heat from the surroundings, and so that's going to end up making the surroundings less entropic or have less entropy, and so that it makes sense that delta S of the surroundings be less than 0 in that case. So then it's scaled by the magnitude of the temperature. If we're at a very small temperature, what you'd see is you get a big jump in delta S. If we're at a very large temperature, you don't get as big of a jump when you have some increment of delta H increase or decrease. And we can imagine that just from the fact that if you're at a low temperature, you open up a lot of different sort of configurations available at very low temperatures that were never accessible. But when you're at really high temperatures, you have so many configurations available that you're adding, you know, maybe a couple million more to something that's a billion. It's not that much of a large change that you would see for delta S of the surroundings there. So let's take a look at whether the Haber-Bosch process is spontaneous at 298 Kelvin. So we have nitrogen plus 3 hydrogen reacting to form 2 ammonia. If we look at the delta H of formation of this reaction, then we get 0 for nitrogen, we get 0 for hydrogen, and if we look for, and that's just because they're in their standard states. And then ammonia, we get minus 46.1 kilojoules per mole. Calculating that delta H for the reaction, it's just 2 moles times the negative 46.1, and since the reactant's all 0, it's minus 0 minus 0. We end up with minus 92.2 kilojoules. So just we made a relationship between delta H of the reaction and delta S of the surroundings. So if we take that delta S of the surroundings, if we're trying to find that, then we just do minus delta H over T. So it gives us 92.2, positive 92.2 kilojoules over 298 Kelvin. Switching that into joules per Kelvin, I end up with 309.4 joules per Kelvin. And so delta S total of this is going to be that delta S of the surroundings, which we said was 309.4 joules per Kelvin, plus delta S of the system, which is something we calculated, I think, like 2 slides ago, as minus 198.7 joules per Kelvin. And then delta S total for this particular reaction is going to be 110.3 joules per Kelvin. And so the entropy for this overall is increasing, and so we can say that this is spontaneous. So what we can ask ourselves, why is delta G our signpost for spontaneity? And it's just because delta G, if we look closely at it, is just rearranged as minus T delta S total. And so if delta G happens to be less than 0, then the total entropy of the system, or the system plus surroundings, is increasing, so it's spontaneous. If delta G is at 0, then delta S total is at 0, and we're at equilibrium. If delta G is at greater than 0, then delta S total is less than 0, and that process is non-spontaneous. So Gibbs energy is sort of a way to follow the entropy of the system plus surroundings, and that's what tells us whether things are going to be spontaneous or not. So looking at this clicker question, it asks us which of the following statements is incorrect. So the first one is, in any chemical or physical process, the total energy of a system and its surroundings is constant. Well, that's the first law of thermodynamics. I expect that one to hold. The second one, it says, any spontaneous process, the entropy of a system must increase. So is that true? That's a little tricky, because we've seen that when the delta S total increases, that leads to a spontaneous process. However, in this one, it's just saying the entropy of a system. And the entropy of a system can still be greater than 0, and we can have a spontaneous reaction because the delta S of the surroundings can be so large in its change to sort of outweigh it. And so, no, this is not true. This should be our incorrect statement that we have here. And so, but the next one, the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. That's the third law of thermodynamics. I don't think we really went over that one. And then the standard molar entropy of 1 mole of the pure substance at 1 atmosphere pressure and a specified temperature. So yeah, the standard molar entropy is just defined as that. So that's true. Okay, so we're going to take a look at a chart here that just sort of illustrates when we should expect things to be spontaneous and not spontaneous, and whether there's a temperature at which they change from being spontaneous to non, or vice versa. And so if we're going to look at just a reaction where we have delta H is negative and delta S is positive, as we do in that first row shown, then what we're going to find is that delta G, if delta H is negative and delta S is positive, is always going to be negative. And so we can guarantee that this kind of reaction is going to be spontaneous at all temperatures. And so an example of some kind of reaction like that is just looking at the NO2 gas going to nitrogen and two oxygens, or a lot of combustions or of that nature. Usually it's something that's creating more atoms or molecules as you would expect, and it's exothermic. So the next one, if we say that we have a positive enthalpy, so an endothermic reaction, and we have a negative entropy, so something that gets more organized, that's something that never is spontaneous. So if you just look at that particular reaction, it's never spontaneous. We have to put some outside amount of energy in order to get that reaction to occur. And so, for instance, that could be oxygen going to ozone. And then if we look at stuff with like a negative and a negative for delta H and delta S, then that's going to lead to something where it can transition from being spontaneous at low temperatures and then going to non-spontaneous at high temperatures. So at low temperatures, delta S isn't much of a factor, and so even though that's a positive contribution to delta G, it's not making it overall positive. But once we increase the temperature sufficiently, the fact that delta S is negative and is going to end up with a positive contribution overall, because that minus T delta S term, it's going to start to outweigh that delta H, which is exothermic, and it's going to become non-spontaneous. And that's something like the Haber-Bosch process that we've been looking at. Another physical process that I think is easy to understand is something like freezing, or freezing a liquid, or condensation. Those are things that happen at low temperatures, but they don't happen at high temperatures. And so the last one being a positive and a positive, so an endothermic reaction with a reaction that becomes more entropic, that's going to be spontaneous at high temperatures, but not at low temperatures. And so the T delta S minus T delta S contribution at higher temperatures becomes sufficient that it makes the overall delta G negative. And this just gives you an example of mercury oxide just breaking down into its constituent pieces, and lots of different things where you're doing dissociations or compositions and other things are often like this, where they're spontaneous at high temperatures but non-spontaneous at low temperatures. So another thing that we might ask ourselves is, we're going from, in at least the last two examples, we're going from something that is spontaneous to non-spontaneous, or vice versa, going from non-spontaneous to spontaneous as we heat it up. And so we could ask ourselves, where does that temperature transition sort of occur? Well, the fact is that if we're going from, take that first example where we have a minus and a minus, and it's spontaneous at low temperatures and not at high temperatures, well, in that case, we know that delta G is initially at a lower temperature going to be less than 0, and then at a point through that transition, it's going to go to greater than 0. So where does it actually hit 0? That's at equilibrium. And so we can always figure out where that temperature, the transition, occurs by just setting delta G equal to 0. And so delta G equals delta H minus T delta S, set it equal to 0. We end up with T equals delta H over delta S. And so in either of those cases, we can go ahead and plug in the values for delta H or delta S, and we can find at what temperature those transitions occur, where they stop being spontaneous or stop being non-spontaneous, depending on the situation. So let's look at a problem where it says, what are the signs of delta H, delta S, and delta G for the following spontaneous reaction of A atoms and B blue atoms? So we see a number of these A molecules or atoms. So we have 6A and 6B to start with, and we end up with 6AB at the very end. And so if I were to look at this, delta S would be the first one that might come to mind. And if we're going from 12 things flying around to only 6, then we can expect that the system is becoming more ordered. So delta S should be less than 0. So what about delta G? Well, it says right in the problem that it's a spontaneous reaction. And so if it's a spontaneous reaction, we should expect that delta G is less than 0. And so if we have that delta S is less than 0 and delta G is less than 0, the only way for the reaction to be spontaneous is going to be if delta H is less than 0, just given the signs. Delta S is less than 0, so that would have had a positive contribution to delta G. Delta H must be tipping the balance to make delta G overall less than 0 and spontaneous. Looking at this reaction, we have basically N2O4 going to 2NO2, and we are given a delta H value of 55.3 kilojoules and a delta S of 175.7 joules per Kelvin. Is this reaction spontaneous at 25 degrees Celsius? How can we figure this out? Well, we know delta G equals delta H minus T delta S, and so I can just plug that in, all those different values there, and I end up, notice I did change the 175.7 into 0.1757 kilojoules per Kelvin, just so the units would work out. And we again end up with a delta G of 2.94 kilojoules. We should expect, if we see that, and it's positive, the reaction is not spontaneous at that temperature. At what temperature does this reaction become spontaneous? So we can look that up or calculate that as well. So T equals delta H over delta S. So we do that 55,000 over 300 joules divided by 175.7 joules per Kelvin, and we end up with 314.7 Kelvin. So let's look at this clicker question. It says, for the rusting iron, which statement is correct? And it gives us the delta H and it gives us the delta S. The first one says the reaction is spontaneous at all temperatures. If you remember back, the one that had a negative and a negative associated with delta H and delta S had a transition. And so this should not be spontaneous at all temperatures. So the second one, the reaction is not spontaneous at very low temperatures. Well, at very low temperatures, delta S isn't going to matter, so we can just look at delta H. And delta H is going to be negative, making delta G negative. And so in that case, it is spontaneous at very low temperatures. So that statement there is not correct. C, the reaction is more spontaneous in the presence of a catalyst. Well, a catalyst isn't going to change the spontaneity of a reaction. Remember, it's just lowering the energy of activation, allowing us to achieve equilibrium faster, but it doesn't change the spontaneity or the delta G in a reaction. And D is delta G is negative at 298 Kelvin. Well, we'll have to calculate that to figure if that's true or not. So we calculate it out, and we get negative 824 kilojoules minus 298 times the negative 0.2475 kilojoules per Kelvin. So notice the units are switched. We get minus 750.2. And so that statement is correct. Another clicker question. So it says, which statement is true about the formation of calcium carbonate from calcium oxide and CO2 at 1 atmosphere? It gives us the delta H, and it gives us the delta S. Again, they're both negative, and so we don't expect it to be spontaneous at all temperatures. Okay, the reaction is spontaneous at high temperatures. If you're looking at high temperatures, remember the one that changes with temperature is that minus T delta S term. And if we look at a minus T delta S there, that delta S is negative, and so when we look at the overall sign of minus T delta S, we're going to get a positive value. Meaning as we increase the temperature, the reaction from an entropic perspective gets less and less favorable. And so it isn't spontaneous at high temperatures. The reaction is spontaneous at low temperatures. Well, at very low temperatures, then delta S is not making a contribution, And so delta H is the one we look to, and delta H is negative, and so I'd expect that one to be the correct one. But let's go through the last two. D, the reaction is not spontaneous at any temperature. We can see that that's not true either from our early discussion. And so C should be the correct answer there. E, just we were able to determine something, so. Okay, so let's look at the standard free energy changes for reactions. So if you remember back, let's just cover what the thermodynamic standard state is. And remember, that's just the most stable form for a substance at 1 atmosphere and 298 Kelvin. And it's referenced as 1 molar for all substances that are in solution. So remember, we just need a baseline for measuring our a lot of our state functions. And this is the conditions under which we look at our state functions and reference them from. So just like sea level is a reference for elevation. So in this one, it says calculate the standard free energy change at 25 degrees Celsius for the Haber synthesis of ammonia, given the values of enthalpy and standard entropy changes. And so we know that it's minus 92.2 kilojoules. Delta S is minus 198.7 joules per Kelvin, and we know we're at a 298 Kelvin temperature. So if we just go ahead and plug those in into delta G equals delta H minus T delta S, we end up with a value of minus 33.0 kilojoules. Is that reaction spontaneous? Delta G is less than 0, so we expect it to be spontaneous. So another thing that we commonly use are these standard free energies of formation. And it's just looking at the formation of 1 mole of substance from its elements in their standard states. And so when we do this, it's just going to be delta G equals the delta G of formation of the products minus the delta G's of the reactants. And we look at our very common reaction that we've been using. And it's going to be very similar to what we did with the delta S terms. And so you end up with a coefficient of whatever substance you're looking at times the delta G for that particular substance. And we're doing products minus the sum of the reactants. So sum of the products minus the sum of the reactants. So another key feature of standard free energies of formation is if we see a delta G, the formation that's equal to 0, then we can assume that that substance is at its most stable form. And you can see in this chart below, we have certain things like nitrogen and hydrogen. Under those conditions for our standard free energies, those things are the most stable substances. So the delta G's of those substances are 0, as they serve as our reference point. So using these values we can get from a table to calculate the standard free energy change at 25 degrees C, we're going to look at this reduction of iron oxide with carbon monoxide. And so again, these are values that we're going to find in a table or in the back of your book, or will be just given to you through the problem. So there's all the delta G's of formation of the different substances present. And again, we're just doing the same thing we do typically, which is just the coefficient times the delta G for a particular substance, and we're doing the sum of the products minus the sum of the reactants. So doing that, we end up with 3 moles times the minus 394.4 plus 0, since that's iron's delta G. And then we have 3 moles, and I should say minus the whole sum of 3 moles times negative 137.2 plus negative 742.2 kilojoules per mole. And so getting or calculating that, we end up with minus 29.4 kilojoules.